Hello, guys. So if you could, of course, please turn on your cameras. I would prefer a class with your faces in it. And several things. First of all, I do know from conversing with a few of you that it's not all that clear for everyone, everything that I have covered. If there is the slightest doubt about any topic, you know that we can talk about it either after class, or if you cannot make it after class, you can just message me and we can consider what other times you might be available. I cannot, unfortunately, be too slow with this material during class. That's why I give you so little time to think about those problems. But we are pretty much finished with chapter 2. Today we are finished with it. We will be finished with it. And I'd like to you to start to be preparing for the exam, and that is to go through the reviews, review questions, prior exams, and see if you can solve some questions that I assigned before. And your exam is, of course, a take-home, so you should not be too worried about it. All right, so just the date. No, I mean, you will know about the date. I will write the exam, I will see what I should ask you, and I'll let you know. And it's a take-home exam, so you have way more time than just 2 hours, okay, to do it. Now, another thing, so just by just writing yes or no, perhaps, or even Y or N, just give me a sense, guys, how do you feel? Do you feel you're on top of the material? Do you feel that most of what I've explained is fairly clear? If so, write yes, and if no, you just please tell me N, and I will have a sense of maybe where you feel you are at. All right, thank you for those that messaged and are messaging. And I like your 70 or 75 or 65. So 60, 65. If there is anything you feel you're confused about, guys, why not talk to me at some point, right? I'm happy to explain it. Good. Now, here is the quiz. We already did the first problem, but let's redo it just to be it's a farewell to chapter 2. So the first question we asked, just quickly, if you can redo it. We have 5 pairs of shoes and 3 individual shoes are picked randomly. What's the probability we have 1 complete pair, and what's the probability we have no complete pair? So A is no pair and B is exactly 1 complete pair. Thank you, Chiara and Gustavo. And I don't remember the numbers. I'm not so good at calculating, but we'll see, Barry, if you are right. And Camille, yes, that's nice for A. So guys, we solved this question indeed. We solved it at the end of last class. And again, first concept, if you get it well, then you can prevent yourself from making combinatorial mistakes, at least some of them. And what we do here is the Kafka protocol that I thought of is, first I will describe the pair number. So what is an individual shoe? An individual shoe is the pair number and left or right. Agreed? So I imagine numbering the pairs 1 through 5 and then writing 1 left, 1 right, 2 left, 2 right. And this is allowing me to create a success protocol. So my success protocol will be listing in order the selected pairs and then referring to each pair which shoe I picked. Is it the left or the right? So that's the way my protocol looks like. So there will be 5 choose 3 possibilities to list the pair numbers in order. And for them, for each number, I have either left or right, and for the next, either left or right. So I have 2 to the power of 3 possibilities. So it's 5 choose 3 times 2 cubed. Agreed? That's my success protocol. I imagined picking the shoes at once. So you have to be careful that the denominator is also doing the same. Denominator means we pick the shoes at once. Now, for the denominator, I might as well list the shoes by population number 1 through 10, right? So 1 left, 1 right means 1 and 2, in other words, right? So there are 10 choose 3 ways of picking individual shoes. And when I simplify it, I get 2/3. So the probability that you pick exactly 1 pair is 2/3. Now, part B can be solved from part A right away because we know that we have odd many shoes. We have 3 shoes that we're picking. So either we pick 1 complete pair or no complete pairs, right? So the probability that we, yes, exactly, Chiara, thank you so much. Then the probability that we pick exactly 1 complete pair must be 1 minus the probability that no complete pair has been picked. So that must be 1/3. But just to play and develop our sense of Kafka protocol, we can do it this way. We can again create a document that talks about success, right? So in this case, success, I pick 1 full pair and 1 extra shoe. So I decided to use this protocol for success. The pair number, and the pair number will indicate the full pair, both shoes, and the remaining shoe, the remaining single shoe. So once I pick a pair number, I have 8 additional shoes to pick from. Do you agree? So it would be 5 choose 1, which is 5, times 8 choose 1. Agreed? So it's 5 times 8. You can see how this document tells me it's 5 choose 8, 5, sorry, times 8 divided by 10 choose 3, and that gives me 1/3. Done. Now, next problem, guys, and again, you can solve it in so many ways, but ideally use some sort of thing that makes you certain you're correct. So we have 7 students and we have to sit them in one row. Exactly 3 students are seated between student number 1 and student number 2. By the way, student number 1 might be here or here, you understand? All that I know is between those particular designated students, 3 are placed, okay? What's the probability this happens? Please calculate. Chara, my impression is that something is missing. So, and of course, make sure you understood my question. Yes, guys? 1 and 2, it doesn't have to be 1 here and 2 here, right? Just there are 3 people between person 1 and person 2. That means they could be like this, right? Just in case it helps. Do Gyong, you look like you have the right answer. At least you have the same answer I thought of. All right, guys, so let's do it together. And this is the situation. So we have students 1 through 7. Okay, you have those students 1 through 7, and we put them into in a row. So of course, Chiara and other people, I think you had denominator correct, 7 factorial. So for the sample space, you can imagine that they can be in any order. You agree? So first could be any one of 7, next any one of 6. So the denominator protocol is very easy. The main protocol is the numerator. Right? How do we calculate numerator? So numerator only considers situations where we had success. Now, what is success? So here is how I decided to describe success. So first of all, I want to know in which relative order do I see people 1 and 2, right? Do I see, forgetting about anyone in between, do I see 1 first and 2 second, or the other way around, right? So I will write it in those boxes. So those boxes, I might have designed them a bit differently, but it should be 1, 2 or 2, 1. So there are 2 possibilities, either 1, 2 or 2, 1. Yes? So it's not really that I have too much choice. Actually, I have either the option of saying 1 is first or 2 is first. And then which individuals were selected to be between them. You see, so that's I call it cluster 1. So cluster 1 is person 1 and person 2, like 2 parts of like 2 bread loaves or 2 pieces of bread. Between them, 3 people are sandwiched. The 3 people that would be sandwiched in order, in this case, I just illustrate the code 4, 3, 7. So let's say 2, 1, 4, 3, 7 means 2 is first, followed by 4, 3, 7, followed by 1. You understand? That's the code. So how many entities can be wedged here? Well, there are 5 possibilities. I cannot select 1 and 2. I have to select 7 minus 2. That's 5. Of them, I choose 3. And to place them in order, I multiply by 3 factorial. So it's 5 choose 3 times 3 factorial. Yes? Do you see that? So that's cluster 1. Now, the remaining individuals are clusters 2 and 3. So cluster 1 is 5 individuals, cluster 2 is 1 individual, and cluster 3 is 1 individual. Together, they make 7 people, right? So then the last part is listing the clusters in order. What do I see first? So cluster 1 is followed by individual that I relabeled as 3. You see, so what is the individual number 3? That corresponds to a person whose number is, well, let's say 1, 2, 3, basically the smallest number that is not included in this region. What is that? So we have 1, we have 2, we have 3, we have 4, so it's 5. So this is individual 5. You follow me?
That looks like 8 people.
Does it? Did I make a mistake? No, because this is this cluster. You don't count all of them, right? It's not this is not all people. This is now clusters. So 5 people were made into 1 supersized person.
And then you have 2 people left over.
Yeah. So the cluster 1 is the cluster that I made with the sandwich between 2 and 1. And then the remaining numbers are relabeled. The remaining clusters consist of individuals, right? So there is 1 supercluster consisting of 5 people, and then you have cluster 2 consisting of 1 person, and cluster 3 consisting of the other 1 person. So together you have 5, 1 plus 1, which is 7. Yes. So this called is not referring to people. I just called it based on how I will see it. So you can see there is a 3 factorial here. So I have 2, 3 factorial, 5 choose 3, 3 factorial over 7 factorial, which if you simplify will give you 1 out of 7 apparent. Okay, so the probability this happens is 1 out of 7. You understand how I did it, guys? Now it's very easy. You see there's a 3 factorial, there is another 3 factorial. It's easy to omit a 3 factorial or to add 1 extra. So if you see a precise code and you understand exactly how you were doing it, how you were counting, you are not confused. So for the exam, I do ask you to do this Kafka protocol, because that's pretty much what I try to teach you. Yes, so when you solve a problem, give me a sense of how you are making up the code, so I'm sure that it's not accidental. Explain it, right? Explain it at least. You don't need to put too many words. In fact, many words are not welcome. You look at the explanation. You see, this is the cluster. Here is the legend below each box, and you can understand how it's built up. Hopefully, you can, right? Good. One more question from this chapter. And this is that question. So New York driver is racing through a school zone at the neck-breaking speed of 26 miles an hour, which is, I think, I forget how long ago they decided to make it a speed limit. So then you have a speed trap located in position 4,1. Now, the question is, if he is racing to this house, located at 7,2, and the trap camera is in position 4,1, what is the probability that he will avoid a fine, given that he always moves each step or each motion, he either moves block horizontally or 1 block up, you understand? So at each moment he decides to either move 1 block up or 1 block horizontally. And he does it randomly. So what's the probability of avoiding the speed trap? A small hint, guys, is focus on the essential. Notice that what dictates where you arrive. It dictates that up to a position how many how many rights and how many up you move. I always confuse between left and right. You know this thing, right? It's my problem. So when I drive, it's very dangerous. I have to think left is where my heart is. Left is where my heart is. But then I don't know if I have one. You have the same problem. No, for me, left is wherever I think is the right way to go. All right, guys, so let's solve it together, I suppose. You look puzzled, and I do wish we spent hours on it, but my experience tells me that this class is too short. So Barry, 1 over this number. Well, if it's true, I'm not sure why. I will check in a moment, okay? If it's true, at least with the protocol, I can tell you what I will do. So guys, what happens if you're moving here? The driver will necessarily get to this home. That's what he is trying to do. So to get to his home, he will have to execute exactly 7 motions to the right and exactly 2 motions up. Do you agree? No matter how you travel, you have to execute 2 motions up and 7 motions to the right. No matter in which order you do that, that will get you to the final destination. Agreed? So so an entire itinerary, the entire journey of the driver can be described by the position. So I can imagine I have 7 plus 2 spaces. 2 of those spaces must be up. They must be selected to indicate up, and the remaining places have to be selected to tell to move to the right. Does it make sense? So I focus on the spaces. So how many spaces are there? Altogether, 7 plus 2 choose 2. So there are 9 choose 2. The choose 2 means I choose which of those are up. So for instance, I might have chosen the first motion to be up, and then 7 motions right, and then the last motion up. You see, so it's up, right, and then up. So that clearly describes one pathway. Do you agree? I could have described up, right. That's a different motion, right? So by using just the letter R and U, or 0 and 1, whichever you like coding, you can figure out all possible motions over this grid. Agreed? So the space is over all equally likely motions, codes where it's made out of U and R, where 2 of the letters are R, and all the remaining 7 of them are right. Sorry. I said two of them are U or up, and the remaining 7 of them are R to the right. So how do I? So that's 9 choose 2. 9 choose 2, and then how many of them get me through the speed camera, right? In how many of those pathways that are randomly taken will there be a fine? To get a fine, it must be the situation that in the first 5 motions, you see this is 1, 2, 3, 4, 5. In the first 5 motions, 1 had to be up, exactly 1. In the first 5 motions, 1 is up, and then in the remaining 1, 2, 3, 4 motions. In the remaining 4 motions, 1 had to be up. Okay, so that's what. So that means that where do I place in the 5 initial motions? Where do I select up? It's either first motion, second, third, fourth, or fifth. So there are 5 possibilities for having the motion up taking place in the first 5 motions. Right? So there are 5 codes where within the first 5 motions you have up, followed by an additional 1, 2, 3, you pass this camera, so it's 1, 2, 3, 4. 4 motions, out of them 1 is up. So it's 5 times 4 divided by 9 choose 2. Those are all the pathways that go through the camera. 1 minus that number are all the pathways that avoid a ticket. Is it clear? So what we get is 5 over 9. So this is 5 over 9, and the probability that we want is 4 over 9. So he has 44%, or roughly 44% chance to avoid a traffic ticket. Good. And now we move to chapter 3. So we have finished whatever we had for exam 1, I think. What we need to know for exam 1. So conditional probability, guys. So what have we observed so far? We have observed that what we really do in probability, we count the number of possible universes. Of course, especially if those number of possible universes are equally likely. If each universe in that collection is equally likely. You can simulate some universes that are more likely by imagining that you have many copies of them, and each copy is actually equally likely. Yes? So roughly speaking, it amounts to counting the universes. Now, if you think about this a little bit, then you realize it's a very monumental and monumentally difficult problem. So because, for instance, suppose that all you're doing is you're throwing a coin. Or you want to know if the coin lands heads or tails. Now, the coin is not by itself, right? When you throw the coin, there are people walking along the street back and forth. It might be raining. Birds are flying in the sky. The sun, the Earth is rotating around the sun, and the sun is rotating in the galaxy, right? So galaxies are moving apart. So the universe is very vast. And why is it that we can exclude some information? And I would like you to think of it in a different way entirely. So you do not exclude information when you do probability. So when you throw a coin, it's not that the fact that the birds are flying in the sky this moment and people are walking on the street, it's not that this is not important. It's that it does not affect probability. So I will show you in this lecture at the end of it how to maybe hopefully better think. Because if you think this way, you will never consider any information as irrelevant. You will just consider this information as sometimes not affecting probability and sometimes as affecting probability, but it's not cause and effect. Understand, guys? The idea that you should have is that every single feature, that every single piece of information gives you a sense of the universe, gives you, it localizes the collection of possible universes in which you find yourself, right? So, and that narrows down the sample space. It's just that the number of universes in which you are looking for the desired property might be narrowed by, let's say, a factor of 2, and the sample space of universes is also narrowed by a factor of 2. That does not affect probability. Or narrowed by a factor of 100, numerator and denominator, does not affect probability, right? But every single information narrows down the number of possible universes, so it cannot be irrelevant. Now, we will tackle that. We will tackle it as we go on. First, let's just for a moment ignore this main difficulty of considering everything and try to understand what is conditional probability. So, what's the probability that an event E happens, but not by itself, given that we know that another event F has happened? And let's make this very concrete. What I mean by that. So suppose, guys, that you flip a coin, not just what I wrote on the board, but you just flip a coin, and it happened that one of the flips, you flip a coin 2 times, right? And you repeat this, you flip a coin 2 times, and it happened that one of those flips happened to be a heads. Good. The question is then, what's the probability that the first flip was heads? Given that in the first 2 throws of the coin, one was heads, what's the probability it was actually, that the first was actually heads? Good? So how can we try to understand how to calculate this probability? So imagine simulating the situation and observing instances where event F happens. Event F is one of the coins lands on heads. One of them lands on heads. So I know. So the way I did it is sorry. So to correct it in my notes, I said F is the event that at least one coin lands on tails. So the same thing I said. So in the experiment, you know that there was a tails in your 2 throws. What's the probability that the first throw was actually heads? I hope I haven't confused you too much. Good. So imagine then trying to simulate those situations and understand what can happen. So here is a simulation in which the 2 coins were thrown 20 times. This is what happened. Okay, and within those trials in blue, I put in a blue rectangle the situation where you had at least one tail. So each big blue rectangle represents a situation where you had at least one tail. Clear? That's the number of occurrences where event F happened. Now I want to know within the occurrences where event F happened, in how many of those occurrences event E happened. And you remember, event E means first throw was heads. Okay, so here is a smaller red box. It indicates that first throw was heads. And so you can see within the blue, you have this red box. So when you have within the blue, you have the red box, that indicates that that event E happened within event F. Agreed? So they both happened. So what does this represent? Blue and red box represents the intersection of those events. Good. So then we can do the following calculation. So first of all, the probability that E happens given that F happens means that F is the collection of all our universes. We know that we are in one of the universes represented in the collection F, right? So in this case, universes are still simple. This universes consists of two values, heads or tails. First, what is first, what's second, right? So we know that F happened if one of those values is a tail. So we know that F is a universe that it's one of the universes. F is either the universe head tail or the universe tail tail, right? That's pretty much, is it? Yes, right? So one of them had to be a tail. So or maybe tail heads. So this is the possible universes where we find ourselves. Agreed? Either we are in this universe or in this universe or in this universe. Right? Within those universes, there is only one. You can see there is only one that seems to be where heads happen first. So the probability of E given F appears to be, if each of those outcomes is equally likely, it appears that there should be 1/3. You agree? The probability that I'm in a universe where the first toss was heads appears to be 1/3. Are you agreeing with me, guys? Now, how do I verify it empirically? Empirically, I will do something like this. That's how we're going to try to obtain this probability in terms of the old sense of probability, in terms of the unrestricted sample space. It's an important formula and we need to understand it. So what I do is I run the simulation and I will ignore everything where that is not contained in a blue box. So you see this is not a blue box, I ignore it. I only count the trials where event F happened. So how many of those trials do I have where event F happened? In this case, I simulated 14 events F. Yes, 14 times it actually occurred. Out of those 14, now since it must be event F, how many of them also correspond to an event E? 7. Right? 7 out of them. So then I consider the running frequency. So 7 divided by 14 is my estimate. Not quite 1/3, it's 1/2 in this situation. But of course, that's only because my simulation is too short. I haven't simulated enough occurrences of event F. Okay, but the idea is you will take that ratio. Does it make sense? You will take the ratio of E intersect F, number of times this occurs, over the number of times F occurs. Right? That relative frequency, here it is. Number of times EF occurs divided by the number of times F occurs, to try to simulate this posterior probability, it's called, right? So we have that something happened and we don't really want to know this probability of E. We want to know probability of E within the universe F, within the set of universes that's restricted F. And similar idea, again, you simulate it, how many times this happens. This formula makes sense to you guys before I move on? Do you understand why I consider this formula? Right? In terms of running frequency, I see if F happens, how does it affect nature's preference for E to occur? Right? And the reason I, of course, calculate intersection of E and F here, that's because if F happened, E cannot happen outside of F. So I only consider elements that are both in E and F. Does it make sense? And then we're going to go back to the general probability. So we get to this formula, guys. So we take limit as this thing goes to infinity. Now, if I divide everything by n and push n to infinity, I get that the numerator is just the definition, the sequential definition of the probability of E intersect F. And the denominator is just the definition for the probability of F. And I get that the probability of E given F is the probability of E intersect F divided by probability F. Look at this formula and think about it, guys. That's an important juncture. The formula has to be strongly making sense. It's based on this philosophy that nature will reveal its preference if you give it many trials, right? So this represents number of times EF occurred divided by number of times F occurred, but I can divide it by total number of trials, including the ones that are discarded. And since in this ratio, I multiply top and bottom by 1/n, I'm not affecting the ratio. But the numerator here represents the ratio that will converge to the probability of EF. And the bottom will converge to the probability of F, and we get this formula. Yes, are you with me, guys? Or have I lost you? All right, think about it very deeply, guys. Very complicated thing. I always did when I first had to consider it. So we're gonna now use this to carry a bunch of calculations. So 2 fair dice are rolled. What is the probability that the first die lands on a 3, given that the sum is 8? We're going to solve it in 2 ways, right? So in 2 ways. So first of all, given that the sum is 8. So suppose that you know that what happened, we threw 2 dice, and we know that the sum on the dice is 8. So we can imagine that this is the collection of universes in which I can find myself. I'm either in this universe or that universe or that universe or that universe or that universe. There are a total of 1, 2, 3, 4, 5 universes. You agree? I'm in one of them. Now, because I'm assuming by symmetry that nature should not have preferred in creating F, there was no preference in which universe was the actual one that I find myself in. They are equally likely. Do you agree? I mean, intuitively it seems. We can try to justify it in a moment. Intuitively, it appears that each of them is equally likely, and only one of those universes has 3 as the outcome on die number 1. So the answer is 1 out of 5. Right? So the probability is 1 out of 5. Now let's verify that we get 1 out of 5 using the other formula, using the unconditional probability. So probability E given F is equal to the probability of E intersect F divided by probability F. Yes? And that's the formula, guys, that you have to internalize. That's what I'm saying. Because if you just use the formula, maybe you'll get to be, you will recognize it by habit, but you understand why that's the correct formula, why it should be the correct formula. Right? So at least in my mind, the limit description of probability gives you a sense why that formula is correct. So we have this. Now, if E and F happened, in terms of set theory, we obviously know that only 3, 5 is both in E and in F, because if in the success situation, first die had to be displaying a 3, and the sum has to be an 8. So if the first die is a 3, then the second die is a 5. So that's the probability of 3, 5. Divided by probability of F, which consists of 5 possibilities out of 36. So this is 1 over 36 divided by 5 over 36. If you multiply top and bottom by 36, you get 1 over 5. So it seems that the result is the same. Good? All right, so here is another question, hopefully not too difficult. We take a fair coin and we flip it twice. What's the conditional probability that both flips land on heads, given that A, first flip lands on heads? Do you understand, guys? So you now know, you threw it twice, and you now know the first outcome was heads, what's the probability that both of them are heads? Okay, okay, good. Yes, we have two tosses, correct, guys? Two tosses, and we know the first toss. If A tells me that I know that first flip was heads, I know the outcome on the first toss. I'm asking you what's the probability that both of them are heads. It's not the unconditional probability. Do you agree? It's I have information. I know something happened, so I actually know that some universes are not possible. So tail is not a possible universe, for instance, or tail heads is not a possible universe. Yes. So just to draw the situation, guys, what happened in A? In A, initially the sample space had several universes possible. So head, tail, head, and tail. Agreed? Now, what happened here is that once I know that one of the first had to be heads, I right away can eliminate this and this. You agree? So those universes are not possible since I know the first outcome had to be heads. And my question is, what's the probability that both are heads? So you'll see that only two universes are left. And very importantly, each of them is just as likely as the other. So the answer is 1/2. The answer for A is 1/2, guys. Thank you. And I think some of you already answered B. What's the answer for B, do you think? So at least one flip was a heads. You don't know which one, but you know that at least one of them had to be heads. What's the answer there? Thank you, Chiara and Ryder. And I see that you're answering it correctly. You can easily see what happens here, guys, right? Which universe do you eliminate? Only one where there are no heads. So you had 4 universes. One is eliminated, the tail universe, right? So you still have 3 remaining universes, and only one of them has both heads. So it's 1/3. You see how you're thinking, guys? You're eliminating universes, and then you see that there's new information, eliminates some universes. And if it's still true that the remaining universes are equally likely, you now have a smaller sample space. And you just count which of those universes in the sample space correspond to a successful outcome. So here it's the same thing that I mentioned, and you can see one is 1/2, one is 1/3. Now, you can of course solve it through the original way, through this formula, with conditional probability, but restricting sample space in this case appears to be the simpler way to deal with it. Now, here is this observation, guys. So if a sample space S has equally likely outcomes, then so is the restriction to any subset. You understand? We're just justifying what we did before. When we calculated 1/2 and 1/3, we assumed that even after some universes were eliminated, the remaining universes, each of them was as likely to occur as another. That's not always the case when you have 3 possibilities or 2 possibilities. Do you agree, guys? You can either today win $600 million or not win $600 million. Those are 2 possibilities, but they are obviously not equally likely. Right? So just because you have certain universes, let's say 2 universes or 3 universes, does not mean they're equally likely. But we're saying this is that if we began with a collection of universes, each of which was equally likely, the restriction to some subset of those universes creates still equally likely posterior sample space. Okay, so that is easy to verify, especially if we have finitely many of them. So assume that we have n universes in total, and something occurs, outcome F occurs, and you have m possibilities in that outcome. So then if x is any element of F, we hope to show that the probability that x occurs is 1 out of m, because it's 1 out of m possibilities. Now, by that formula Px given F, we have probability of x intersected with F divided by probability F. Now, x is a singleton belonging to F. So this is just the probability of x divided by the probability of F. What's the probability of a singleton? It's 1 over n. What's the probability of F? It's m over n. So that crosses away the n's and you get 1 over n, just as we argued. Do you understand what I just said? We're just very carefully just established that restricting the sample space does not generate anything odd. It's okay, we can work with it safely. So here is the next question, guys. See if you can solve it. And here, you need to learn to be good with symbols. Here is another type. So first was Kafka Protocol, and now being able to give good assignments to situations that happen. So student is taking 1 hour exam. The probability that the student will finish the exam in less than X hours is X divided by 2, where X is between 0 and 1. So in other words, the probability the person finishes the exam, this student is not so strong in the material, because the probability the student finishes before 1 hour is gone, that he needs to take the full hour, is 1/2. So at least 50% likely that the student is not done when the time is up. So it's X over 2 in general for any time. Now, given that the student is still working after 0.75 hours, what is the probability that the full hour is used? You understand the question, guys? So the student is working after 3/4 of the hour still, and that happened, you already observed it. What's the likelihood now that the student will have to use the full hour? Perhaps. But it's good, it reminds you of stuff. Mostly Andrew. All right, guys, let's look at it together. So here is the idea. You have to train. The next thing to train is representing events using sets. So here is what we know. We have fx, f sub x is the event that student is finished in less than x hours, right? So that means student is finished. So we want the probability student is not finished in 1 hour. You see how I can describe it? F sub 1, finished in 1 hour complement means not finished in 1 hour. Given that student is not finished in 3/4 of the hour. Yes? Now, by that conditional formula, that's the same as the probability of the intersection divided by the probability of the prior event, the event that occurred. Yes? You let me know, guys, if you're very confused or anything, please, right? So, since I really want you to grasp this formula and have a strong sense of it. So what is this? What's the intersection of not finishing in 1 hour and not finishing in 3/4? Obviously, if you have not finished in 1 hour, you haven't finished in 3/4 of the hour. You agree? So the intersection is, this set is smaller, right? The possibilities of all the people that don't finish in 1 hour also have not finished in 3/4 of an hour, which means all the universes in which the student is not done after 1 hour are subsets of universes where the person is not done after 3/4 of the hour, which this is the intersection, yes? So we have this ratio. Yes, eliminate possibilities where you finished before, right? So the complements, it's a bit tricky. It's very easy to be confused here, right? But the way you should think of it is just, okay, you have all cases where student does not finish in 75% of the hour. Yes. Now that student still has a chance to finish. So you have universes in which a student that does not finish in 75% does finish in 85% or something like that. But you never have universes in which somebody does not finish in 1 hour and yet finishes with some smaller percentage of the hour, right? So that means that F1 complement is a sub-collection of universes. It's a sub-collection of destinies. They are more narrow destinies than not finishing in 3/4 of the hour, right? Almost no student finishes in 0 hours or right away, right? And then you have more definite destinies as time progresses. So this is the ratio that we are looking at. Now, what is this? This is simply 1 minus the probability of finishing within a 1 hour, and the denominator is 1 minus the probability of finishing in 75% of the hour. Now, what we know is the probability, if I know this number, I just divide it by 2. So the number is 1, I put 1/2. The number is 3/4, and I divide it by 2, so it's 3/8. And then I multiply everything by 8, and I get 4/5, or 80%. You see, guys, initially, you should have expected that the likelihood for the student, basically, that's why it's so nice that when you're young, you can be anything, right? You can be a firefighter, a cosmonaut. Well, you cannot be a cosmonaut anymore, but and then as time goes on, your chances, your possibilities are narrower and narrower. That's the same thing that you're observing here. The student initially had a 50% chance of finishing in 1 hour. Now the student only has 20% chance to do that. That makes sense. The more you observe that the student is not done, the more you're convinced that it will not happen. Good. So the answer is that the probability that he's not done by the end of the hour is 80%. Right? Here, let's consider a few more questions, guys. This one is interesting. Let's see what you would say about this one. The crown prince is always the oldest male offspring in a royal family. The family has 3 siblings, 3 children. What's the probability that the crown prince is the oldest child? You understand? You know that the family has 3 children. What's the probability that the crown prince is the oldest? Let's see if you can calculate it. Okay, thank you, Nicholas. Always be careful. As I advised you, create Kafka protocols. Think about this question. Well then, guys, well, let's see the answer, I guess. Okay, here's my Kafka protocol. Now, my space has to have at least one male heir. You agree? So then either I have an oldest male heir, and that's the first box. That's what the first box represents. And then the remaining two children can be anything they want. So there are 4 possibilities for the situation. Or the oldest child is a girl, and then maybe the middle child is the male. And then I have remaining 2 possibilities. Or both oldest and middle child are girls, and the remaining child is a boy. You agree? So that involves one universe. So there are 7 equally likely universes. You see, Nicholas, 7 equally likely universes. And then the probability that the crown prince is oldest is 4 out of 7. So the answer is 4 over 7. Did you expect that, guys? And do you agree that the answer is absolutely correct? Taurus, you don't agree. Why not? I mean, we have all sorts of complications, especially in the modern day, apparently. Right, in the modern day, I mean, this problem is unsolvable. But eliminating, we make several assumptions. You can make it with coins or anything else, right? So we have 3 coins, and the first throw of the coin is special, right? In that situation, obviously, the first throw of the coin, if it lands on head, is crown prince. If you put it in that framework, then you have 7 equally likely universes. And we have 4 of them where the first is special. You see why 7, guys? Because altogether, we are claiming that we had 3 coin tosses. Altogether, we could have had 8. But we know that we don't here deal with a situation where we have all tails. It did not happen that it's all tails. So we have 7 universes, actually. Right, 7 universes, and each of them is equally likely. In those universes, 4 have this interesting outcome. Yes, good. Now, for the next thing, guys, how many of you recognize what this is about? Young Dolores sees a strange man, her mother's new tenant, looking at her through the living room window. Each of his first and last names is either Humbert or Quilty. She knows one of them is Humbert. What's the probability that his full name is Humbert if she is wearing one of 3 pairs of her favorite sunglasses, pair numbered 1? If you want, we can listen to Nabokov speak at the end of class, in case you have never heard him speak. I just wonder, why do people don't speak this way nowadays? Even in Russian, by the way, he has a strange accent. It sounds like he's learned German. Well, people don't read anything these days, Barry. Yes. Yes. So what's the probability his name is Humbert? Very good, Nicholas and Gustavo. And Barry, you are even better, right? Because you read the book. So this is the situation, guys. So in this case, this extra information that she is wearing sunglasses is not going to influence probability, because in our sample space, our universe, it looks like that. It's first name, last name, and sunglasses. So there are three possibilities for the sunglasses. And we know this is filled in with number one. And this could be any one of two, and this could be any one of two, but we know one of them has to be Humbert. So there are actually three possibilities, and that makes up 1 out of 3 universes, Nicholas. Correct? So in this case, the sunglasses do not influence the probability that the person is named Humbert. Now, next and last question for today. Your neighbor has 2 dogs. Each dog is either white or brown. We assume that it's equally likely to be white or brown for each of them, right? And each dog eats 1 of 3. We can eliminate the word favorite if you prefer. Just eats 1 of 3 dog foods. Now, so then you have never seen those dogs. You just heard the rumor that your neighbor has them. Maybe it's in the south, and you don't really want to see dogs in the south. They would bark at you. So, suppose that you are seeing a brown dog eating his particular dish. Let's say dish number 1, right? And the dog is brown. The question is, what's the probability both dogs are brown? You see, you observe the dog. You know, each of them eats 1 of 3 types of foods. You're observing one dog that's brown and eating food number 1, let's say. Good. What's the probability both dogs are brown? Okay, Gustavo says 1/2, Barry says 1/2. Okay, we'll see. We shall see. Some people say 1/3. Okay, Gustavo, but you're making an assumption that numerator is 1. So Barry says the favorite dishes are irrelevant. The brown or so some people say 1/2, some say 1/3. All right. Well, congratulations, guys, because none of you are correct. So here is what we observe. And again, we did see that before. It's not a new question. Well, nobody is. In probability, guys, nobody is ever correct. And if you actually look at what's happening today, it's impossible to be correct. The things that have so many interesting interpretations. Yes, so many interesting interpretations. I can suggest a video. YouTube has, I think, synchronous translations in German. So maybe if you're interested, I can show you a video and ask you, what do you think? I actually even considered making it an assignment for your class because I'm a sadist, you know. But we'll see. So anyhow, so here is the situation. So you have old dog or young dog, let's say dog 1, dog 2. Okay, so what have you observed? You might have observed first old dog eating. So you see, you have in general, before anything is happening, you have two possibilities for the color of the old dog, two possibilities for the color of the young dog, and three possibilities for each of their foods that they might be eating as their favorite food or as the only food that they really like to eat, right? Out of three. So we might have made this observation about the universe, brown one, or this observation about the universe. So altogether, we are witnessing one of 11 universes. One of 11 universes. Now, the one universe where both dogs are brown has in this case either this universe or that universe. So there are three possibilities for each, minus 1, 5. So the answer is 5 out of 11. I mean, I could have worded it better, but you understand the idea, right? You can simulate it by coins. The probability that both dogs are brown is 5 out of 11. Do you understand why? Some of you say irrelevant, but my point is, guys, nothing. The reason we would have ignored the glasses that Lolita was wearing in the previous problem, Dolores was wearing, only because that did not influence probability. That did influence which universes we're witnessing, but it did not influence the ratio of universes of success to total universes. Here, it does. It would have been 1/2 if I knew that the dog I'm looking at is the older dog, for instance. Good. And on the first day of class, I believe we solved the same problem with the two children. With age or whatever else, is because in this universe, you can imagine listing them according to some property as first dog, second dog. Yes, first dog, second dog. And then either you witnessed the first dog or you witnessed the second dog. And that affects which particular observation you have made. Your universe, your restricted universe, is information about both dogs and the foods that they are eating. Right? So you can say favorite, or maybe the dog refuses to eat anything else, but as far as you know, it's equally likely to refuse to eat any type of food. Right? So it only likes to eat, let's say, one food out of 3 given to it. Good. And so what we have afterwards, we're going to talk about it, I guess, next class, is what do you do with the information? Do you discard information? How is it that you are supposed to think about conditional probability? And as I mentioned in the beginning of class, you don't discard anything at all. Look at it. I did not ignore that Dolores was wearing glasses. Do you agree? Look at my form for the Dolores. I said sunglasses, right? I did not dismiss that information. Some of you think, oh, the sunglasses that she is wearing is not affecting the name of Humbert. But that's because you're thinking in casual direction. You're thinking that wearing glasses will have influence on the name. But what you should be thinking is that the glasses she is wearing identifies the particular universe where you find yourself. You're all watching Rick and Morty, or I'm assuming, right? So it's similar like that. They are parallel universes, and the glasses a person is wearing might tell you something about the universe, which it does. The only problem is that it's not influencing the probability. Understand? Every information will tell you something about the universe, but some information will not have an impact on probability. Right? Because look at it. If I don't mention the glasses, then how many universes do I have? I have the universes times 3. Right? So here I have 2 possibilities, and 3 possibilities. Right? So if I have this information, I divide by 3. If I don't have it, I don't divide by 3. But numerator and denominator in both cases will be divided by the same factor, by 3. That's not going to influence probability. Do you understand? That's what we're going to develop intuition for it. All right, guys, thank you so much for staying. Well, here you go. And Barry says she was also chewing gum. I don't remember that, but that obviously influences probability. Not always in very obvious ways. Maybe it affects the probability slightly. You can go crazy thinking about it. Take care, or stay with me and get weirder. Bye.